Okay, we're going to look at one more limit example. This is a really interesting example, actually. So for this function, you should be able to look at this function and recognize that 0, 0 is not in the domain of the function. And in fact, that's the only point that's not in the domain of the function. So even if we were not told to consider this limit, this is the relevant limit to consider for this function. And we're going to try some different things here. Polar coordinates probably does not work great for this problem, even though we're approaching 0, 0, because I don't have an x squared plus y squared here. I don't get the nice simplification that we got. So we're going to try looking at some different paths of approach toward the origin here. So I'm just going to draw a little picture over here to help kind of orient ourselves in terms of what we're doing. So we're going to just consider some different paths of approach. If we consider this limit as we come in toward the origin along the x-axis, so along the x-axis, y will equal 0 and x will approach 0. Okay, so I'm just going to go across here and write this. I know I wrote them up and down in the last video here, but we'll let x approach 0. And remember, y is going to be actually equal to 0. So on the numerator, we'll have x squared times 0 over x to the 4th plus 0 squared. So again, I'm going to simplify, simplify, simplify on this function and then worry about the limit at the end. So x squared times 0, that numerator will just be 0. On the denominator, I'll have x to the 4th. And again, here I have something where the numerator is actually equal to 0 and the denominator is just really close to 0, just approaching 0 but not equal to 0. So a fraction where I have the numerator equal to 0 and the denominator not equal to 0, that fraction will just be 0. So the function, after I made that substitution, just simplifies to 0, so that limit is 0. All right, so there was one path of approach. Another path of approach to consider might be along the y-axis, where x is equal to 0, x is equal to 0, and y is approaching 0. So I wrote x equal to 0 there. Sorry, that got a little messy. Okay, so we're going to do that, and you might be able to see what's going to happen here when we do that. Just see your way through the problem a little bit here. When I let y approach 0 and x actually equals 0, I'll get 0 squared times y, which will just be 0 on the numerator. And on the denominator, I'll have 0 to the 4th plus y squared. So I skipped a couple steps this time. Instead of substituting in, I went right to that next step. But this simplifies to 0, and so the limit as y approaches 0 of 0 is 0. So I got the same limit along another path of approach there. So might be worth asking at that point, so does that mean that this limit is actually 0? And it's not, actually. Let's go look at the graph and see what's going on there with the graph. Okay, so here I've graphed our function, z equals x squared times y over the quantity x to the 4th plus y squared. And you can see from looking at this graph that when x and y are close to the origin, when I'm coming in along the x-axis, it's behind that little ridge there, but those z values, our work showed that those z values are approaching 0. And when I come in along the y-axis, those z values go right in that little fold of that surface there, and those z values are approaching 0. But you can see these places here where the z values appear to be approaching some positive number and some negative number down here. And so from the graph, it appears that that limit does not exist. It's just a matter of showing it. So this is a harder problem to show that this limit does not exist, but there are a couple of features about the graph and about the function equation that can kind of give you some clues about where you might go with this. What I need to find is another path where I get a different answer, something other than 0 for that limit. And you might notice here on this graph there are these ridges that appear to be kind of in the shape of a parabola. And another one down here that appears to be kind of in the shape of a parabola. So let's go back to the board and look at look at the function here. So we looked in the graph and we saw some parabola shapes that appeared to be places where the z values are maybe approaching something else. So from looking at the graph, but also from looking at the equation, and noticing on the equation here that there's some sort of symmetry in the equation between x squared and y, right? So x squared, and then this is x squared squared, and y squared. So there is some sort of symmetry in the equation between y and x squared. So even if you didn't see those parabolas in the graph, noticing the equation symmetry related here between y and x squared might lead you to think about trying a parabola as another path of approach. So let's do that one here. I'm going to pick just kind of the most basic parabola along y equals x squared. So you need to make sure that if you're picking a path of approach, that your path that you're choosing actually does approach the point you're supposed to be approaching. So if my point that I was supposed to be approaching was, say, 0, 1, then y equals x squared is not a good path because that does not approach 0, 1. But the parabola y equals x squared does go through the origin, and so I can come in along that path of approach. So algebraically, I'm going to do something that's pretty similar to what I did here. I'm going to substitute and then let the other variable approach 0. So I have some choices about how I can do that, and either way you should end up with the same answer here. I could either substitute x squared in place of y, and then I will have all x's left and let x approach 0. Or I could substitute y in place of x squared, and then I'll have all y's left here, and I can let y approach 0. So whichever way you want to do that, but you're essentially converting this to a single variable limit kind of problem here. So I'm just going to do the whole problem in terms of x's. You're probably used to doing things in terms of x's anyway. So along y equals x squared, so I'm going to force all x's here. So I will just be letting x approach 0. All right, so I have the x squared that's there, and then I'm going to have, in place of the y, I'm going to substitute x squared. And then on the denominator, I have the x to the 4th that was already there. And then in place of y, I'm going to substitute x squared, and then that will be squared. So I will get x to the 4th. OK, so here I'm going to get some simplification, and then I will worry about the limit. So on the numerator, x squared times x squared is x to the 4th. And on the denominator here, I have x to the 4th plus x to the 4th, or 2x to the 4th. And you can certainly skip some steps of algebra here as long as you do them correctly. So I have x to the 4th on the numerator and 2x to the 4th on the denominator, and that all reduces to 1/2 without worrying about what x is approaching. So I got 1/2. And the key thing then is that 1/2 is different from what I got on these other steps here. So I don't really need all of these paths that I chose here. I need 2 different paths. So once I got a different answer, because I have 1/2 that is not equal to either of these values, 0. I got different limits along different paths of approach that would show that this original limit here does not exist. And actually, our textbook does this problem, and it does something interesting with this problem that you might look at in our textbook. It actually shows that along every line, it uses y equals mx. Along every line that goes through the origin, straight line, y equals mx, for any value of m. When you use any path of approach y equals mx, you will actually get 0 for all of these limits along any line y equals mx. And so the important part of that is to understand that even if you get 0 along infinitely many paths of approach, if that's not every path of approach, then you really haven't shown that the limit exists, right? So to show that a limit does not exist, you really just need 2 different paths that do not agree. So here I have 2. To show a limit does exist, you don't just need infinitely many paths that give you the same answer. You actually need all paths. So if all of your infinitely many paths is not every path, then that's not enough to show. So although this is what our textbook does, and they make an interesting discussion around that, I want to emphasize that checking y equals mx is never enough to show that a limit does exist. If you check y equals mx and you get the same answer along every line, that's never enough to show that a limit does exist, because that's not all paths. And it's overkill for showing that a limit does not exist. You really just need two paths along which you get different answers. So although this is an interesting discussion that our textbook does with this y equals mx, it's probably not a good strategy for solving most of the problems that you will work on, because it's overkill for showing that a limit does not exist, and it's not ever enough to show that a limit does exist, because there could be other paths along which you get different answers. So I encourage you to read that discussion, but really as you do your practice problems, remember that you either need to choose all paths, which we've done that sometimes by using some algebra simplifications or some polar coordinate simplifications, or if you're trying to show a limit does not exist, you really just need two paths, right? So I don't really need this one here. I just did that as kind of some extra work to emphasize that that's not enough. You just need to find at least two paths along which you get different limits.